Hello class. As I said at the end of the second lecture, today we will start to talk about resizing images. We will talk about zooming and shrinking. Zooming is a method of increasing the size of a given image. Zooming can be viewed as oversampling or upsampling of a given image. Shrinking is actually downsampling of an image. And we have talked about the downsampling when we were talking about sampling and spatial resolution. We have seen we use resize in order to reduce the number of samples and see how it affects on the spatial resolution that we have. So today we will talk about zooming or upsampling. Now, when we want to do the zooming, there are two important steps that we have to consider and we have to do. Now, first is we have to create a new pixel location. We want to do the zooming, so we want to make it twice, 3 times, 4 times bigger. So first, we have to create the locations, which lots of question marks are there. We don't know what is the value, so we are creating the locations. Second, now in these locations that we have created, we have to assign new grade level value. And we insert this new grade level values to this location by using interpolation. Interpolation is defined to be the estimation of the value of unknown points by using the value of known points. We know two knowns or couple of known values, and then we try to estimate what are the unknown values in between. Of course, you may remember from mathematics we have extrapolation, which again we have no values and we try to guess what is the next value out of the range of these values. Interpolation is the value between the known, estimating the unknown value between the known values. Now if you go to the IEEE Explorer and if you only search on journals, you will see that in the last 4 years, over 450 journal papers have been published in IEEE regarding to introducing new interpolation techniques. Now, Young in 2004 and his colleagues published a paper in the International Society for Photogramming and Remote Sensing entitled 12 Different Interpolation Methods. Now, we will not talk about them in details in this course. We will only refer to the 3 very well-known conventional methods. But I will talk about the name of these 12 methods so your ear will be familiar with them. And you see that we have lots of interpolation techniques. Well, based on different applications, some we favor a few more, but you can also still work on developing an interpolation technique so people with a math background can work and attack on this issue. Now, in the Young paper, the first method which was mentioned was the inverse distance to a power method. And it is basically a weighted average interpolator. The second technique is the kringing method. And kringing is a geostatistical grading method. This method produces visually appealing maps for irregularly spaced data. The third technique is the minimum curvature method. And the interpolated surface generated by minimum curvature is analogous to a thin linearly elastic plate passing through each of the data values with the minimum amount of bending. This is how the minimum curvature method's name comes out. A minimum curvature is not an exact interpolator, though we use it as interpolator. We know that in image processing and information theory, there are lots of techniques, lots of mathematical representation, which are not exactly one thing, but we use it in there. Like Kullback-Leibler divergence, it's not a distance, we use it somehow as a metric of the distance. The first method is the modified Shepard's method. It is very similar to the first method, the inverse distance to a power interpolator, but in a modified Shepard's method, the local least square has been eliminated. The fifth method is the natural neighbor method. The natural neighbor interpolation algorithm uses the weighted average of the neighboring observations, where the weights are proportional to the so-called borrowed area. Then the sixth method is the nearest neighbor method, and it assigns the value of the nearest point to each grid node. This method is useful when data are already evenly spaced. In considering an image, if we have lots of squares in the image, you will see that the nearest neighbor interpolation will give you visually good image, though it is not a very appreciated technique. The seventh method is the polynomial regression method. Polynomial regression is used to define large-scale trends and patterns in the data. Polynomial regression is not really an interpolator because it is not estimating much of the data, but it tells you a very nice trend, a very nice formula and curve, which you can use in order to find out what is the unknown intensity value that you need to find. The eighth method is the radial basis function interpolation method, and it is a diverse group of data interpolation methods. All of the radial basis function methods are exact interpolators. You can read more about them by referring to the papers which are talking about the radial basis function interpolation. I will try to put and upload a few research papers on that technique in the website, so you can download them and you can read them. Now, the ninth method is the triangulation with linear interpolation method. This algorithm creates triangles by drawing the line between the data points. The original points are connected in such a way that no triangle's edges are intersecting by other triangles. So there is no intersection of the edges. This method is again an exact interpolator. Triangulation with linear interpolation works best when data are evenly distributed over the grid area. The 10th method is the moving average method. The moving average method assigns value to grid nodes by averaging the data within the grid nodes search elements. We will refer to the moving average method later in order to remove some noises. Not for the interpolation, of course. Now, the 11th technique is the data metric method. The collection of data metric methods creates grids of information between the data on a node-by-node basis. And finally, a local polynomial method. And it assigns value to grid nodes by using the weighted least square widths with data within the grid node search elements. So there are, as you can see, many techniques. However, in this course, we will refer to three main types of interpolation techniques, which are namely nearest neighbor interpolation, bilinear interpolation, and bicubic interpolation. So we will see a little bit about the details of them. We will see what are the differences. The nearest neighbor, as the name stands, we look at the neighbor and we pick up the nearest values. The bilinear interpolation, it tries to fit a linear surface or a linear curvature among the data that we have. Well, you can have a 2x2 or 4x4 neighbors, and then you consider these 2x2 neighbors and you fit a linear relation between them. That's how we are estimating. And in bicubic, what we do, we are using like 4x4 neighbors, so the total of 16 pixels, and we are fitting a third degree of polynomial in order to find out what is the unknown values. Now here in the slides, you can see the photo which has been produced by, has been zoomed by using a nearest neighbor, by bilinear, and by bicubic techniques. As you can see, well, in the nearest neighbor, it produced some checkboards or blocking effect. And this is not good. This technique, as I referred before, is good for images which we have lots of rectangular in it. But it is the fastest method ever, because you don't need any calculation. What is your neighbor? Put it in. What is your neighbor? Put it in. The second technique was bilinear interpolation. And as you can see, bilinear interpolation produces a smoother image, and it is an anti-aliasing technique. This blocking effect is called aliasing, so we don't have any blocking effect in the bilinear, so it's an anti-aliasing technique. And bicubic produces a sharper image comparing to the bilinear. It is also anti-aliasing. And in many image processing techniques, that when you read a research paper, they use the bicubic interpolation. We of course have SP-line and so many other techniques which you can always search about them in IEEE Explorer and read more about them. So in today's lecture, we talk about the interpolation and zooming, and you have seen how mathematics and image processing comes together. The mathematic things that we know can be applied in image processing. Now again, I have put some extra material on the web which you can download them and use them and read them. I hope that you enjoyed this lecture. See you in the next lecture.